This is Mark Summers again from Summers Technical Services. I'm going to do part 3 of our simulation static analysis on our I-beam. So let's go back and see where we left off. So here's my model. I've done the analysis, run my analysis, and we want to interrogate this and see if it matches with our hand calculations we did earlier in lab. So the deflection looks reasonable, that it's deflecting this way, maximum near the middle. And here's my values, but I don't like the display in millimeters, so I just right-click on Displacement Results, Edit Definition, change it to inches, and approve that. And I'm seeing I got about 7/10 of an inch deflection. Seems like a lot, but it's a 25-foot long I-beam, so that seems reasonable to me, and it seems reasonable that the displacement changes as I get closer to the middle of the beam where the maximum moment is. So I think I believe my results. Now I'm going to go ask for some stress plots and compare those to my hand calculations. Well, the Solidworks is set up to give you 3 default result tabs: von Mises stress, displacement, and strain. I don't want von Mises stress. I want my normal stress in the z direction because that's what I'm creating with my bending moment, the way the beam is loaded. And so I'm going to come over and revisit my stress element cube. And this orientation is the same as it is in my model. And so what I want is the sigma normal stress on this z face. And so that's what I'm going to ask for. So I right-click on this result, edit definition, change it from von Mises stress to sigma x. And also while I'm in here, I'm not going to want this megapascal display in metric units. I want to change it to psi and approve that. And now my results look like this. Now when you're looking at results on simulation studies, you want to be very wary of any stress results near locations where you have concentrated loads and or constraints. But since my stress is in the middle of the beam here, away from any concentrated forces or boundary conditions where the fixtures are, I believe these numbers here. And I believe them even more so because they're nice and smooth. You can see here where the load's added, I can't believe these numbers here because it's too much going on. There's too much of a concentrated load there. But as I get away from that location of the concentrated load, these loads spread out and more accurately are reflected in the model. And so right here in the middle of the model, this should be in compression and the bottom should be in tension, and that's what I'm seeing, negative 20,000 up to positive 20,000. And so this looks like good results here. And the other thing I like about these results is that it very closely matches my hand calculations. My hand calculations came up with 20,205 psi, which is almost identical to these values here. So it looks like I've successfully demonstrated that my normal stresses on my model match very closely with my hand calculations done previously. So let's do some similar analysis on the shear stress we need to calculate. And so I don't have a shear stress over here, so I'm going to right click on the results and say define stress plot. I want to define a new one, and I want to change it to shear stress. And looking at my orientation here, I want this shear stress on the z plane in the y direction. And so I pull down, ask for tau zy, and I see there is no tau zy. Well, if you remember, there's 6 shear stresses, but there's pairs of them that are equal. So let's go again, go retrieve my cube here. And if I'm looking for tau zy, which is this one right here, I can see that tau zy is also equal to tau yz due to my equilibrium conditions on my stress cube. And so I can ask for tyz, and it'll be the same value as tzy. So tau yz, I'll look for in here. Tau yz, there it is. I want to change this to psi again, so it matches my units of my hand calculations, and I'll approve that and get that stress plot. Now, contrary to what we had on the normal stress, is that this maximum shear stress is going to be near the end over here because these are where my maximum shear values are on my shear and moment diagrams. And I'm getting a lot of non-real results here right at the very end here where I have my constraints here. So I don't believe the shear stress at this point right here is as high. I don't believe the model. And so what I'm going to do is change the range here so it eliminates that high spot that's not real and gives me a more realistic look at the shear stress. And so I'm going to right click, edit definition on this edge here, and my hand calculations I did earlier, I came up with a shear stress, maximum shear stress of about 2565 psi. And so I want to come in here under chart options, and instead of automatically defining the maximum and minimum values, I want to change these values closer to what I'm expecting on my model. So 2565, I want to make this 3000, and I want to make the lower limit minus 3000, and then see what the results look like. So I'll approve that. Sure enough, this change here looks good. It looks realistic. Here I've got almost constant shear across this face here, and I've got constant shear across this face because the shear force is the same across this length. I'd expect the highest shear stress to be along the neutral axis, which it is. And so these values seem reasonable to me as well. Right here the shear abruptly changes, but along this piece of the web the shear stress should be constant, VQ over IT, because V is constant. Between here and here there's no additional load, there's no additional shear. From here to here there's no additional shear, and so it should be a constant maximum shear along the neutral axis, varying slightly going up and down, but not very much. And then from here, once this load starts going in here, I get a varying shear stress because the load is varying, the shear, the V value is varying. And so I can go in here and interrogate the results here right along the neutral axis on my beam on this end by going to Plot Tools and Probe, and I can click a few places along this face here, see what they look like. And sure enough, these shear values are all about 2600 psi, which matches very nicely with my 2565 psi maximum shear stress that I calculated on my hand calculations. So that takes us to the end of our simulation video. I hope you enjoyed it and learned something, and subscribe to my Summers Technical Services YouTube page to see more videos like this using Solidworks simulation.